Thank you, Andreas, for the nice introduction. I decided to go for this particular subject today. It's awakening, so how to predict the effect of external stimulation at the whole brain level. In particular, because this is the result of a collaboration that we ran together with Morten Kringelbach, who is also in the audience, and especially with our honored person, Nikos Logothetis. You know why? I'm not from California, so I jump and I give you. And I think it's relatively new, so it was published a couple of weeks ago, and I hope that will be interesting for most of you. So in order to study stimulus-driven transition between different brain states, our approach is, or our belief, is that before doing this empirically, we need to understand what is going on first at the theoretical, mechanistical level. And this is the reason why we study all this business in silico, in the framework of theoretical models, but are not unrealistic theoretical models, are models which are fitted to the reality of fMRI data. I divided the talk in two parts. Because we need to understand mechanistically those transitions, I have to review very briefly the subject of whole brain modeling. And I will try to do in a very rapid and criminal way from a unifying perspective. And then the second ingredient is, because we would love to achieve the transition between different brain states, is to know what is a brain state. I am aware that the next talk is exactly about that, but I will give a proxy from a quantitative, dynamical point of view. So before I start with the serious part of the talk, what the motivation and what we have in mind, when we speak about the external stimulation-driven transitions, we have in mind electrical or electromagnetic stimulation in a translational context most of the time, in a clinical context like DBS or TMS. Another philosophical slide before we start, and I think it's particularly relevant, because the style how we will try to study this particular transition is a little bit different than what our intuition will indicate us. So let's assume for the moment that we have in this cartoon a healthy brain with a healthy dynamic. I don't want to do any claim here about the dynamic. It could be an attractor dynamic, a multi-attractor dynamic, a stochastic dynamic, chaos dynamic. I don't care. I just put it a beautiful, colorful landscape, just to not say any word. And then I can represent this with a landscape, and there is some working point, which means normality. Of course, if for some reason, because there are an imbalance of neurotransmitter or disconnections patterns or whatever, the dynamic is distorted and I get a disease working point. And the intuition would say that, okay, I need to try to apply an external stimulation in order to try to reestablish, to control, in particular, the working point and try to go to the situation of the normality. So, and there are many groups following this type of strategy. So trying to apply a control, technically, a control strategy to recover the working point. This is not what we are doing. What we are doing is we have the disease brain, and what we are trying to do is to design a stimulation such that the landscape of the dynamics, such that the dynamics is recovered. And then per se, the dynamic will go to the right working point. And if we believe in homeostatic plastic recovery processes, then the system will stay there for a while or forever. So this is the general philosophy. So first part, let me tell you a couple of words about whole brain modeling. The main idea of whole brain modeling is also cartoonized in this slide, and somehow is we try to describe the global level of the dynamics, so as observed by functional methods, for example, fMRI, from the underlying local dynamics and the interconnections between those local regions. so which is given mainly by the anatomy. So somehow the whole brain model tried to integrate the structural connectome, the structural connectivity describing the anatomy, who is connected with whom, and to explain how from this interconnection between the local dynamics emerge a global dynamic which is given in form of the functional connectome, which is describing the functional correlations between the activity label. There are many models which are able to explain this relationship. Of course, I mean, I didn't say, but I think it was clear. I mean, the goal is to try to explain the true, which is what you measure at the level of the fMRI, for example, the functional connectome, the functional connectivity matrix. You want to explain that with your model. And there are many ways to explain or to fit relatively well the empirical functional connectivity. For example, I divided this in 3 different types of scenarios. The first scenario is very simple. It's extremely simple in the sense that if we have the anatomy, and by definition, we have a very simple type of dynamic because we are studying resting state, and it's just a noisy dynamics, because we are interconnecting those different sources of noise, then we introduce correlation. Those are the models that were formulated mainly by Arnaud Messet, and that works pretty well. So basically, there is nothing complicated here. It's just noise plus anatomy. Of course, you can be a little bit more picky and say, well, the level of noise, or the way how I describe the noise, should be biophysical realistic. And there are many ways of describing that. So you can get now a bunch of spiking or Hodgkin-Huxley neurons with a realistic synaptic activity and so on. And you can prove that there is a particular working point where the dynamics is also perfect, where the dynamic fits the functional connectivity. Of course, this is different than this. The level of fitting is the same, but the level of explanation is different because this is working always. This is only working in a very particular point, which is at a critical point. It's at the edge of a bifurcation. I'm not going into the details here, but just the level of explanation is different. There is a third scenario where instead of using just asynchronous noise at the level of your spiking networks that you are describing, you assume that there are certain level of oscillations. And this is what we call, in contrast to the first and second scenario, which are noisy scenarios, the oscillatory or the oscillation scenario, where we insert oscillation. And again, here there are a very particular point which give an explanation of the FC in a total different orthogonal way. Now what we have are cluster synchronizations, and those cluster synchronizations are metastables, and they switch from one to the other. So we have 3 different ways of explaining exactly the same at the same level of accuracy in totally 3 different orthogonal ways. What that means, Houston, we have a problem. I mean, that was shown empirically, of course, by Messet. And what you have to see here is that the level of explanation by using all the different noisy or oscillatory models is basically the same. So the intuition behind that, why that could be the case, was actually presented in that seminal paper from Mauricio Corbetta and Marcus Reichel. Was a very important paper because was the first time that resting state with fMRI was evidenced in primates, was under light anesthesia. And what you see here at the left, a typical resting state network. It's a visual motor network with the monkey light anesthetized. If the monkey is awake and performing a visual motor task, you see basically the same. But the most astonishing part is here, because what you see on the third panel is the anatomy. And it's astonishing overlapping with the resting state. So that means if you are not so wrong, you cannot destroy that. That means that the underlying anatomy is practically determining the functionality. From that point of view, modeling is not so useful. But what we claim is that anatomy is shaping the dynamics and not determining the dynamics. And there are many evidences of that. My favorites are here. When you compare the relationship between functional and structural connectivity, as I told you and I showed you before, it's very overlapping, so it's very high. But the level of correlation change and the different brain states. For example, in the paper of the neurospin of Paulo Bartfeld, they have tested functional connectivity, and of course the structural connectivity is the same because it's anatomy, of the monkey and the different level of anesthesia, including wakefulness, and the level of correlation increase with the level of unconsciousness. The same happens in humans in sleep. There are the papers from Helmut Slauf and Enzo Tagliasucchi, and exactly the same effect happens. When you are in deep sleep, the relationship between function and structure increase respect to wakefulness. So what that means, there is something more than just shaping with anatomy the dynamics, and there's some freedom for modeling to find the truth. In fact, and this is one of the main slides from the modeling point of view. What we do is we use a model which is flexible enough to include all scenarios. And instead of imposing a scenario from the beginning, guided by our intuition, which most of the time is wrong, we try to find the right scenario by fitting the data. So what we need is, of course, the flexibility that the local dynamic now at each local region is such that is able to describe a fixed point plus noise, so meaning noise scenario, or an oscillatory scenario. And there is a mathematical form, I don't go into the details here, that describes exactly that transition in the most simple way. It's called normal form, that means simple in mathematics. And this transition from fixed point or from noise to oscillations is a Hopf bifurcation. And this is what we insert. And then we try to fit exactly at what level or at which kind of working point we are able to explain the empirical data. This is one very important ingredient, so a very flexible model able to describe all the scenarios, not fixing the scenarios and trying to fit the valid scenario. And the second ingredient is the functional connectivity was always so easy to explain because it's a very simple measure. It's a grand average measure. So during 20 minutes, 30 minutes, or whatever is the length of your resting state, you are forgetting the time and just calculating the computation. So you are losing a lot of information. And because of this triviality is the reason that even very simple and wrong models can explain the functional connectivity. So an idea to go over that problem was to include the time. It's fantastic, eh? In 2013, Neuroimage discovered the time. And that was in the lab of Vince Kalun, in the seminal paper of Allen et al. And the idea was very simple. I mean, instead of using a huge window, you just use a small window, typically it's half minute or 1 minute, and you slide the window, and you consider how the functional connectivity that you calculate in that sliding window change across time. These are, by the way, real data from Petra Ritter from La Charité. It's a particular subject, and what you see is really in this sliding window of 1 minute or 2 minutes, 2 minutes in this case, how the different elements, which are picked randomly, are changing in time, how the matrix is changing in time, how the principal component of that matrix changes in time, just in order to show that those spatio-temporal fluctuations are relevant. You can take that into account relatively easily, and this is a paper that we have done a couple of years ago together with Victor Girsa. So taking this idea, we define now a new matrix, which is not the functional connectome, it's the so-called FCD matrix. It's a time-by-time matrix where time is the position of the sliding window, and the corresponding elements are just the correlation or the overlap between the different microstates. So let's assume that those sliding windows are defined in some way a microstate in order to distinguish this from the state, from the brain state. And then here you are just seeing the overlapping. So this is a real matrix of a particular subject of the group of Petra Ritter. This is from the modeling. And what you see here is this typical checkerboard type of architecture. So meaning here you have a microstate, is alive, then is gone, to another microstate, different from that. Therefore, you have blue, and then it's recover, and then it's gone again, and then it's recover. So you get this architecture. So in order to compare different subsets or subset models, because they are not aligned in time, but at least you have the statistic of all those elements, and you put those elements in an histogram and just compare with the typical distance between histograms, like the Kolmogorov-Smirnov distance, how well you are explaining now this spatio-temporal fluctuation. It turned out that the Hopf model, let's concentrate first here on the right, when we check the functional connectivity or when we check the functional connectivity dynamics, now we have the two parameters, one which is the Coma parameter, which is the general conductivity value of the fibers, so the coupling parameter, and the other is the local bifurcation parameters. For the moment, assuming that they are equal, this is just a simplification for pedagogical reasons. The nice thing is that if it is negative, you remember you were in the fixed point region, so you are in a scenario 1. If you are in the positive range, you are in a scenario 2, but now you have the freedom to see where you want to be, perhaps between a scenario 1 and 2. And in fact, the best fitting, so the maximal correlation of the functional connectivity and the maximal explanation, so the minimal Kolmogorov-Smirnov distance of the FCD is exactly at the edge of the bifurcation. So meaning that's exactly at the mixture between both scenarios, the noisy scenario and the oscillatory scenario, you get a fantastic explanation of the FC. Here are 3 cuts for the noisy, the bifurcation, and the oscillatory scenario of the FC. You see, they are all good, they are all more or less reasonable, meaning that it's not so informative, but when you go to the FCD, then you discover that only this scenario at the border of the bifurcation is able to explain the spatio-temporal fluctuation. So we have now a relatively powerful model which is able to explain not only the grand average functional measures like the functional connectivity, but also the spatio-temporal fluctuation in terms at least of the FCD. Now the question is, okay, we want to use this as a mechanistic model for trying to stimulate and see the effect of the stimulation and see even more if we can stimulate in a way that we can provoke a brain transition. So the second big problem is, what the hell is a brain state? One candidate is, if you are very naive, one candidate is FC. I hope that I spoke already 20 minutes. I hope that I convinced you that FC is not a good idea. FCD seems to be a good idea. I was involved in the definition of FCD. It should be a good idea. It's not a good idea. So let's go for a better idea. And the better idea is really to take those microstates now more seriously, and the description of the temporal permanence in those states also more seriously. More seriously means probabilistically. And this is what we call a probabilistic state space approach, or shortly PMS, a probabilistic metastable state approach. I will explain why I use the word metastable. The idea is very simple. You have your signal, could be Vol, could be EMG, could be EEG, and what you do in order to avoid the sliding window, you just extract the phases, and for each time point, you define a matrix which contains the difference of the phases. So in this way, you avoid really to having to decide on the width of the sliding window, which is a critical point, which can be handled statistically, but okay, it's much easier if you get away from that. And then that means that practically at each point, at each TR or at your sampling rate, you have a snapshot of the state of synchronization of the whole brain. So this matrix contained in a given parcellation, of course, but could be fine enough. I mean, nowadays we're using the Glaser parcellation, which have like 300, 400 regions. So you have a snapshot of the whole brain. Then there are a step which is optative. Sometimes we do, sometimes we don't do that. And if you reduce the dimensionality, because if you have 400 regions, you have to reduce the dimensionality by using the first leading component. But this is anecdotic, it's not necessary. The second really serious step is we clusterize those snapshots. We clusterize those matrices. And that means that basically you have to decide, of course, on the number of clusters, and there are some methodologies for that. In general, we use the minimal number of clusters which are able to describe well the data. And here you can imagine that there are some centers or 3 centers where around those centers there are regions where the state of synchronization is similar. And then you are switching from one state to another state, so from one center to another center. This is the reason why we call metastable state or metastable microstate, if you want to be more redundant. And the last step is to transform this nice graphic now in numbers. And transforming this in numbers means you can calculate now, if you concatenate your session, if you concatenate your subjects, you can calculate the probability and the probability of transition. In particular, this profile of probability or these matrices of probability of transition is what we claim is a proxy, a quantitative proxy of the description of the underlying dynamics of a brain state. I was very careful. I didn't say what is a brain state. So, but this is what we will take as a definition, as a quantitative definition of a brain state. This is just to, before I go to the real business, just to show that this approach works very well. Last year we actually it's really an astonishing result because we studied data, Coma data, from 4 different labs, from Paris, from Liège, from New York, and from Toronto. You see there from the name of the people, Lionel Nakache, Steve Laurie, Adrian Owen, and Nicolas Schiff. And we have done exactly this PMS approach, but the trick was that we use it only the Paris data. And then we fix the cluster, and we use the same cluster for all the other patients with other scanners, other type of person, other type of doctors, other type of classification. And what you see here are the 3 different brain states, the 3 different levels of consciousness of coma, so vegetative, minimal consciousness, and recovery, and the different states. So you see 5 states, and some of them, this in particular and this in particular, they are significant relevant. So they can distinguish perfectly in all 4 labs the different labels, the different brain states. Okay, now we have all the elements. We have the whole brain model, the mechanistic account of what's going on when we apply an stimulation, then we can follow and we can describe mechanistically what's going on. And we know what we want to do. We want to perform this transition from one state to another state, and we have a relatively good proxy for a quantitative definition of that transition. So we, as a proof of concept, what I am showing you now is the results obtained with data from Helmut Slauf and Enzo Tagliasucchi, collected in the Max Planck in Frankfurt. They are very good data because they collected this simultaneously EEG and fMRI, so meaning that we have access to the functional connectivity dynamics and so on, or the probabilistic state space approach, and also to the real classification of the EEG. Here are, as you see, the 2 states that we took, wakefulness and deep sleep. So this is the so-called M3 state. And what you have to see here, so forget the transition matrix because you cannot see it too much. I mean, there are differences, but here is more clear in the profile of the probability on 3 different clusters. This is the empirical data, and what you have to see that's the empirical data for, so the PMS description for sleep and for wakefulness are different. Good. We can distinguish that. Yeah. And the second interesting effect is this and this are very similar, and this are very similar, because this is the model. Good. Means that we were able to fit the model in order to adjust to the probabilistic state space description of the empirical data. So, and now the key issue is on the top. we have a model, and we have done this first for sleep. We fit the data, and then you are not allowed to touch any single parameter of the model. The model is like a real brain. You can do nothing. But you are allowed to stimulate this from outside. And in fact, by stimulating this from outside, of course you will change the dynamic. This is trivial. You don't need to solve any differential equation for that. But in many different ways. So what you want is to find where to stimulate in such a way that your target state, so your source state was sleep, and your target state should be wakefulness. If you manage to do that, at least in silico of an empirical fitted model, you were able to perform what we call awakening, which is, by the way, motivated by coma patients and many other type of patients, by the way. This is the way how we do that. It's very simple. We have, you remember the Hopf model, and what we take is one region. Actually, we do bilaterally, but this is as a matter of simplification. It's not essential at all. And what we do is, for a while, so for some time, we artificially move the local bifurcation parameters to the positive region. So we introduce oscillations in that particular region. And this is what we call synchronization protocol. Or we do the contrary. We go to the very negative values, meaning we destroy oscillations. We introduce noise. And this is what we call noise protocol. This is the synchronization protocol from sleep to awake. And the color, so this is the label of modification of the A going into the right position, so synchronization protocol. These are the areas, so we use it in this case AAL, which has 90 different cortical, subcortical regions. And this is for stimulating one by one exhaustively each different areas. And what you see is that if you don't stimulate, so if the stimulation is 0, the color, which is the level of fitting of your target state, is bad. It's bad means it's too high. Of course, because you are modeling in a sleep state and not an awake state. But then when you start to push in some of the regions this to the right, you reach the blue region. And the blue region means that you are doing a very good job. So you manage really to perform the transition from the deep sleep to the wake without touching parameters, just by external stimulations. This is exactly the same, but now with different combination. Of course, I have shown you before sleep to awake. You can do from awake to sleep. If you do sleep to awake, only the synchronization protocol works, and the noisy protocol does not work, and the other way around from the other condition. And of course, you can graphic, because here all the colors is very similar, but of course, you can amplify that and see really who are the particular regions, cortex of subcortex, which are promoting at best a particular transition from one brain state to the other brain state. I would love to finish with a last point. Until now, I mentioned that we were studying the effect of external electrical stimulation, in silico, of course. Of course, not all external stimulation or not all stimulation need to be external and need to be electrical. And in particular, we considered here pharmacological stimulations or pharmacological manipulation, if you want. We were lucky because we had access to data from the Imperial College, from Robin Carhart-Harris. Robin Carhart-Harris has done resting state, the different conditions, but mainly manipulating placebo conditions with psychedelics. So he used LSD and psilocybin in order to induce psychedelic states and study at the brain level what's going on. So fantastic data. On the other hand, through a collaboration with Gitte Knudsen, we were able to get access to PET data describing the density of serotonin receptors. It is well known that psychedelics, and in particular LSD and psilocybin, are mainly addressing serotonin receptors. So the idea was now, in the framework of the model, to introduce this information. Here we are not using the Hopf model, we're using a much more detailed biophysical model, which includes explicitly pyramidal and GABAergic neurons, also very realistic synaptic dynamics, and so on. I say it's anecdotic, it's not anecdotic, but anyway, I don't want to explain that it is now. And we modified the gain of the different neurons according to the density of receptors. Of course, that is a free parameter, I mean, because which is a scaling parameter, and we don't know at which level we are. But we can fit that because we have the data. And this is what is shown here. So first, we do what we do always. We fit our global coupling parameter, so our parameter, in order to fit the placebo data. And this is the model that we cannot touch anymore. But this model contains now the serotonin receptors. But the scaling parameter of the serotonin receptors is 0. So we have this level of modeling for the placebo, this level of modeling for the LSD. And now we start to increase that. And what we see is this. It's extremely beautiful. So we improve the label. By the way, here is FCD. The same happens with PMS. We increase the label of fitting of the psychedelic data. It's not, we not see the same with the placebo, which is really what we expect. So meaning that really when we excite the serotonin receptors, we catch this in the mechanistic model. In order to be sure that it was not just a problem of overfitting, which is clear here that it's not overfitting. But anyway, we shuffle the receptors, the PER receptors, many times. I don't remember how many, 100 or 1,000. And we see that we destroy the fitting, because the fitting is not so good as before. Even more, because from PET we have really all possible receptors, or we can put uniform information artificially. We also divide it between training and test, because the referee asked it for that. But as you see here, just by eye, it's always worse, because it's well known that LSD is not really related with the 5-HT1B or with the 4 or 1A. It's with the 2A. It's with the 2A, so very specifically. And my last slide, this is also, by the way, another paper that we published together with Nikos a couple of years ago. And the last point that I wanted to stress is we can do better. And this doing better is not just because we want to fit better. I always teach that to my students. I mean, everybody believes that the business of computational neuroscience or theoretical neuroscience is to fit good things. I mean, it's not to fit, it's to understand. I mean, and the fit is just an excuse for understanding. So here we wanted to fit better because we wanted to investigate a very particular effect, which is cartoonized here. The idea is exactly the same as before. We integrate now in the framework of a whole brain model anatomy, dynamics, functionality, and neurotransmitter information, so PET information. But we have done this before passively. So we say we have the serotonin receptors, we activate them, they just regulate the gain, and that is. So the only dynamical system, the only thing moving across time was the neuronal system. But we know that the neurotransmitter system is also a dynamical system. And we wanted to study if we can express minimally these dynamics of the neurotransmitter system. And we decided to do this through the release and reuptake dynamics, which is very well known. It's the so-called Michaelis-Menten equation. But that was also not the main point. The main point is that now I have both dynamics, and I know or have certain ideas or hypotheses how to couple them, and I want to study if the coupling is really necessary or not. And what we see here in terms of the PMS in this case, and in terms not only of the probability but also of the lifetime, are two cases. So the no dynamic case is like before. In reality, it's not exactly like before because the model is more detailed. Now, instead of touching the gain, we touch really the excitatory synaptic synapses. But let's say for the moment, from the pedagogical point of view, it's the point as before. So it's a very good fitting. It's much below 0.05. I mean, it's doing a good job. It's good. We didn't publish anything wrong, Nikos. So that is good. But we can do better. And by doing better, we learn that the coupling of the dynamic, so the entanglement between the two dynamical systems, is absolutely fundamental. And funny enough, I speak for myself, I am a physicist by formation. I mean, I should have started thinking on that since 30 years. I don't know why I have never done this. Of course, we have two dynamic systems, and we were always obsessed only with one, the neuronal system. Perhaps because most of the data are coming from there. But the take-home message is, I believe it that I was over time. I am fantastic, I have 3 minutes, I can do a job. Take-home message, I hope that I managed to convince you that the absolutely necessity of doing first these in silico models, not only because are translationally relevant for the design of the logic of stimulation, even more if we discover that for some diseases there is no one logic but many logics, or multi-site stimulation. But to understand really the effect of what we are doing, because if not, it's all chemistry. I mean, and I agree that we should do all chemistry because chemistry came from all chemistry, but now we have all the elements in order to study mechanistically in an approximation, of course, what are the effects of what we are doing. And the second take-home message is that we started to do that because the neurotransmitter manipulation is a real empirical manipulation that we were able to explain. So, thank you for your attention.
Thank you very much. I think we have time for a couple short questions before we need to go into our last session.
Thank you. Gustavo, this is pretty fascinating stuff. But which kind of anatomy do you incorporate in the model? You know, because there are so many anatomical parameters that you can think of.
Yeah. Very good question. I mean, at the moment, when we do humans, we use DTI tractography. We know all the problems that DTI tractography has. And even model can be used in order to solve some of those problems. So, in fact, we can use the DTI tractography as a kind of a priori and then try to measure that. In the case of animals, of course, there are nice cases like the mice. We have the anatomy given by the Allen Institute, which is pretty detailed, but it's even referring to fibers. In the case of the monkey Hopf, we have not for the whole brain, but practically for the whole brain, the Kennedy architecture, which is also is very realistic. But the important part of the question is, this is only one aspect of the anatomy. Of course, it's the most simple, or we believe it, and I still believe perhaps was the most simple, and therefore we started by that. Now we are going beyond that. because, and that was the take-home message of the neurotransmitter business. So we learned that the heterogeneity matters. So now I express this in other words. Perhaps the anatomical heterogeneity matters even more. So perhaps I need really to know how many neurons or proportion of pyramidal neurons, proportion of GABAergic neurons, cytoarchitectonic architecture, etc., which are data that are slowly available. So the next plan is really to incorporate. So the key word this man in my lab is heterogeneity, and we mean anatomical heterogeneity.
Please.
I was wondering what is the relationship between the microstates that you have shown with fMRI and the ones that have been shown with EEG. Although the time scale is very different, I was wondering whether there is some kind of relationship.
We are working on that because I am very lucky and we manage, but was casualty because I started this before that, but we got a project together with the Swiss people. The whole story is coming from Geneva. And with Michel, I mean, we are studying exactly that. So we have data where we have combined the EEG and fMRI. He's applying his methodology as a first approach. I think we should really be harmonic in the type of clustering that we use. But as a first approach, he would apply on the EEG the standard microstates that he always observed and try to see the correlations with the bold one. I don't think that there is a strong relationship with the bold one, but if we do the same business at the level of MEG, which is a thing that we have to do, by the way, then I expect that there should be at least a correlation. I hope there is more than a correlation. But,
right, I see no further questions, so thank you very much again.